Here's a little pro tip for you. When edge finding near a corner, once you've found your edge, either shut the mill off at this point or pull the material directly away from the edge finder before moving laterally, or else this kind of thing can happen. Not to worry, the edge finder was just fine. Only my pride was wounded. Hello Internet, my name is Quinn and this is Blondihacks. I'm working on the Pennsylvania A3 switcher this week and we're going to make the Crosshead guide rails. These look like very simple parts, but the details matter, and importantly this is going to connect a whole bunch of previously unconnected moving and stationary systems, which means there's a whole pile of new constraints to resolve. And if we've made any mistakes so far, we're about to find out. The Crosshead guide rails run from the motion bracket across to the back heads on the cylinders, and of course support the crosshead and prevent any vertical motion that would tend to happen from the main rod pushing up and down on the crosshead. While these are simple steel bars, every single dimension on them is critical for the crossheads to run well. So we're going to take our time, and the devil is in the details. Also, because these are fairly simple parts, it gives me a chance to show you some of the more detailed aspects of the work that don't usually make the edit. To make these bars, I have some scraps of 4140. This is a very nice machining and very high quality, very strong steel. Should be great for this purpose. These are offcuts from some other pieces that were normalized, and that's important because these pieces are going to be machined very, very thin, and if they weren't normalized, they would tend to warp. Normalizing the steel means heating it up to a cherry red and then letting it cool down slowly. And what that does is relieves the internal stresses that cold-rolled material has put into it by the steel mill, and that's what causes the warping when you start machining it. Normalizing is not typically necessary before machining, but it is pretty important when doing thin parts like this because that's where the warpage really becomes an issue. Now, I started out by working on these in pairs, trying to machine 2-dimension in one long strip, but it didn't work very well. There was too much material sticking out the edges of the vise. So I decided to go back and cut them into 4 pieces ahead of time, and I'll machine them in 4 pieces. Because I need 4 of these, and they need to be as accurate as I can make them and as identical as I can make them, I'm taking my time, keeping an eye on taper, that kind of thing, and we're going to do some setup techniques to improve our efficiency a little bit. The first piece has been machined down to what I think is final dimension on one axis, and that's the critical sliding axis. I'm going to test fit that in the crosshead, make sure that's a nice sliding fit in there, and that looks really, really good. This tells me that my dimension is good, so if I can bring the other 3 to this same dimension, I'll be in good shape. Now comes the efficiency part. I've got the head still sitting at the final 0 value that it was at when I machined that first one, so if I machine the other 3 down to that same 0 value on the CoolDRO, then I know all 4 will be that same dimension, and they should be identical. Doing lots of inspection here to prove out those assumptions, and that seems to have worked well. Now for the other dimension, I'm going to actually do this in 2 setups, which is a little fussy, but you'll see why in a second. So everything gets clamped up nice and tight, and I machine down to what's quite a thin dimension on this axis, just 1/8 of an inch thick. This is likely where I'd be paying the price if I had not normalized this material ahead of time. I would have little banana-shaped crosshead guide rails at this point, and I would probably be starting over. I have done that many times. You've seen me do that on this channel. I've scrapped many a part because I tried to be lazy and didn't normalize it beforehand. You'll note that this second last pass is very close to the top of the vice jaws, and that's why I need 2 setups for this final axis of these parts. I brought all 4 parts to within one finishing cut of being the final dimension, so there's one side there still unmachined. All 4 of them are at this stage, and what that allows me to do then is do the finishing cut on all 4 of them with a slightly taller set of parallels. These taller set are holding on to like 7 molecules of steel. It's a very, very thin grip on top of those vice jaws, so I didn't trust it for doing the heavier cuts that were needed to bring it to within finishing cut distance. But now I don't need to take a heavy cut, so I can just skim the final side of all of these parts in this flimsier setup, let's say. maybe it would have been okay, but you can see how little material is being held in the vice jaws. And then finally the ends get cleaned up and everything brought down to final length. Another challenge with these thin parts is that my beloved Heimer cannot edge find on them because the ball on the Heimer is too big, nor can I get in on the edges of the vice jaws because the parallels are too close. So it's old school time. There are still a few things that these old mechanical edge finders can do that the mighty Heimer cannot, and one of them is edge finding on a very thin edge that is sticking up above the vice jaw. The reason for the edge finding is that I can get some holes drilled in the ends of these bars. Each bar has a threaded hole at one end and a clearance hole drilled at the other. Use of the end stop there, of course, because I do have 8 of these holes to do. Somewhere between tool changing and part changing, there's a sweet spot for a given operation for efficiency, and I seem to be landing on head moving as being the deciding factor. If you can do a tool change without moving the head, then it's usually quicker and easier, I find, to leave the part in there and do all of the steps before changing parts. However, for tapping, for example, that requires moving the head, so I do all of the tapping at the end. Drilling holes is the fun and exciting part, so that always makes the edit. All of the deburring and cleaning is less fun and exciting, so that tends not to make the edit. Every single time you see me drill a hole on this channel, I then go and deburr both sides of that hole and use the little air puffer to blow out any chips that might be in those holes, especially for threads. For these tiny, tiny threaded holes, there's often a little chip in there that you can't even see that will prevent the screw from threading in nicely, so it's really important to keep everything clean and chamfer those edges nicely. There are so many little finishing steps like that that go into these parts that never make the cut because, well, you'd be watching the same stuff all the time for every part. Now then, for the other end, the nice thing about an end stop and a symmetrical part is that you can just flip the part around and you don't have to move the head of the mill or the table, and you can drill the other hole. There's the 4 guide bars functionally complete. Now, however, you might notice that we're only 7.5 minutes into this video, so what else is there to do? Well, for one thing, we got to make a bunch of bolts. I decided to use hex head bolts to mount these because they're going to be visible, and hex heads will look nicer than giant machine screws. And well, one thing you spend a lot of time doing in model engineering is shortening tiny screws. This is my little screw shortening fixture. It's just a piece of aluminum angle with a bunch of tiny threaded holes in it of various sizes. I can thread the bolt or the screw into it the desired length that I wish to cut off, and then I actually do the cutting with a fret saw. I've tried lots of different methods of shortening tiny screws. I've tried machines and different fixtures and different types of saws and snips and so on. For my money, this works the best. It's really fast, it's easy, it's repeatable, and it does a nice job. You may not have thought much about it, but every single bolt and screw on these models pretty much is a custom length. These tiny screws and bolts really only come in 1 or 2 sizes for a given thread pitch, because there's really no point in trying to stock every possible size that you could possibly need, even if you could buy them in all those different lengths. So they really only come in a couple of long lengths, and you're expected to cut them to suit your application. Next comes what I call the fittin' and fettlin' stage, wherein physics laughs at our CAD drawings. Even if you make every part completely 100% dead nuts in the middle of the tolerance, everything's perfect, it's still not all going to bolt together like Lego. You will still need to fit things and file things a little here and there. For example, these little L brackets that hold the ends of the guide rails have a fillet in them because of the nose radius on the milling cutter that was used to make it. There's no such thing as a 0 nose radius cutter. So that is not going to seat perfectly in there right off the bat. We need to do a little bit of needle filing to get rid of the fillet on the inside corner of that bracket left by the end mill. It's also sometimes necessary to chase your threads one more time with a tap just by hand. Oftentimes the chamfering process will chew up the top thread a little bit, or there might be a little bit of debris in there. People often tell me, oh, you should chamfer before you tap, and then that doesn't happen. Well, maybe that works for 1/2 inch 13 holes in 1 inch steel plate, but at this scale that does not work. The tap chews up your chamfer and you end up redoing the chamfer anyway, and then the chamfer borks up the top thread. In my experience at these small sizes, it's better to tap first, then chamfer, and then sometimes you need to chase the thread one more time, but only sometimes. Then once everything is fitting together smoothly between all of the individual components, then I know I can start final assembly and then start debugging the final assembly, which of course, that isn't necessarily going to go smoothly either. You see all the stuff I added out for you? Test fit time of the crosshead rails. Let's see how they all go together. It's looking pretty good so far. One end gets bolted to the back head on the cylinders, and there's 4 bolts that hold these pairs of rails together. So of course I'm just loosely bolting everything together at first on both sides, and then everything will get snugged up at the end, just like any complex assembly. You don't tighten the bolts one by one, or else you'll never get everything to line up properly. The whole assembly is going to have some position where it wants to kind of sit, based on the accumulation of all the tiny mistakes that you've probably made. Keeping with our behind-the-scenes theme, here's how I actually get shots like that. Yes, I spend a lot of time with a camera directly in my face. But hey, after a few years of doing this, honestly, you hardly even notice it anymore. With everything assembled, I can now start snugging things down, kind of going a little bit at a time, all the way around the mechanism, just like you would with a cylinder head or any other complex assembly. You want all of these parts to kind of settle into each other nice and square and have everything sit where it's supposed to. Okay, first test roll. Now it's time to find any tightness or binding that might be in this mechanism. And there is definitely some. I would expect it with an assembly like this where we're bringing together all of these different moving parts that have never been joined to each other before. There's a lot of constraints on this system, and everything has to be perfect for there to be no binding. There is some tightness and some binding, but step 1 is to oil everything and make sure that it isn't just friction that's causing everything to drag a little bit. Now begins the debugging process. A complex mechanism like this has many, many possible sources of tightness and binding. There's a lot of interactions between all of these components, and like any complex system, like say debugging a big piece of software, you have to break it down into smaller pieces. You have to eliminate the variables. You can roll it back and forth on your bench all day, and you're not going to intuit where the tightness is coming from. You have to start disconnecting things and isolating subsystems to figure out where the tightness is coming from. The first step is to make sure everything's sitting where it's supposed to. In this case, you can see my subframe is actually floating about 22 thou above where it's supposed to, just due to how the bolts tightened down. So I clamped the subframe down against the frame, and actually the mechanism got a little freer, so that's a good sign. It was still tight though, so the next step to eliminate some variables is I disconnected the piston rods. We'll eliminate that whole set of variables with the stuffing boxes and the pistons and the rings and so on. And now it moves extremely freely. So that definitely helped. It's so free now that I can actually spin it, freewheel it, if you will. So it's definitely the relationship between the piston rods and the crossheads that is at issue. That, of course, makes perfect sense because with the crossheads disconnected, there's really nothing constraining the horizontal motion of the crosshead because the main rod pivots at both ends. So if the crosshead guide rails aren't perfectly parallel to the piston rods, it doesn't matter until the piston rods are connected. While doing that, I did notice one thing. The freeness of the mechanism depends on the position of the suspension. Turns out I have an interference between the motion bracket and the tires at full suspension travel. So that's definitely something that needs to be fixed. There's no point in doing further testing until you resolve each issue that you find, because that issue is going to interfere with any other tests that you might want to do. I pulled that motion plate assembly off, did a little bit of filing, and now I've got clearance at full suspension travel. That's one problem eliminated. At this point, I feel pretty good with where things are at in the sense that the remaining problems are solvable. So I think that it's time to permanently attach that motion plate assembly to the frame. It seemed like the easiest way to do this was to just place the entire locomotive on the mill table rather than disassembling the entire frame. Just got to get it level, make the noise. Beep. I just barely have room to get in there with the clearance drill and mark those holes. I'm not going to try to measure anything. Where the bracket is currently seems to be where it wants to sit based on the lengths of the crosshead rails. So I just marked them where they sit, and now I can pull the frame out of there and do the tap drill size and the actual tapping of those holes. From the DRO, actually, they came in very close to where they should be based on the hole pattern of the motion plate, so I feel pretty good about where these holes actually landed. With that assembly permanently bolted in place now, we can start doing some final debugging of the last couple of tight spots. There's still, I think, 2 little tight spots remaining that I don't think will run in. The difference between a tightness and something that will run in is kind of experience. A little bit of observation revealed one additional problem. If I put some tissue paper between the main rod and the bracket, yeah, either that's hitting or it's clearing by less than the thickness of the tissue paper. I'm going to put my money on it's hitting. So a little bit of filing cleared that up, but it was only on one side and the mechanism would push through it. It was just grazing it, so that tells you how close it actually was. But that's one more tightness eliminated. This rolling on the bench, by the way, is quite a good test because when it's just rolling on its flanges like this, there isn't a lot of traction. So if there's any kind of tightness or binding, the wheels will slide because the fairly low weight of the locomotive at this point is not enough to force the mechanism to roll with so little traction on the surface. One tight spot remaining. A good diagnostic tool is to just start loosening things until the mechanism works better. You can see I've got the wheels locked up at a tight spot. Now watch what happens if I push the locomotive while I loosen this bolt. All of a sudden, it starts rolling. So I know that that bracket being bolted down is causing something to get tight. And in fact, you can see as I tighten this bolt down that the crosshead rail is being pushed down at this end by about 6 thousandths. And that's with the crosshead in that position. So before the bolt is tight, the rail is sitting where the crosshead wants it to be. So we know that it's the bracket being tightened that's pushing it out of position. The solution to this seemed pretty simple. I took the bracket off and filed a little bit, just a few thousandths of material off of the underside of the upper bracket. There was no point in doing the lower bracket because that bracket being pushed down can only make the mechanism looser. So I just freed up the top bracket a little bit, which technically means the brackets are maybe slightly out of parallel at that end, but not enough to matter, and it should be enough to free up the mechanism. Now you can see when I tighten that down, that rail doesn't move. Maybe half a thou. We'll go ahead and call that bearing preload and ship it. That was the big ticket tightness, I think. The mechanism now moves smoothly throughout its entire motion. There's a little bit of drag still that I believe is coming from the piston rings. I can't quite freewheel it by flicking it the way you can with the pistons disconnected, but I wouldn't expect that to be possible. I mean, there should be a little bit of drag from the piston rings or else they're not doing their job. But it feels like to me that it is moving smoothly, and any little bit of drag that's left is just going to be what will run in. Again, the difference between binding and tightness that will run in is kind of experience. You build a few engines, you start to learn the difference. Now that everything's fitting, the last little bit of finishing I do is I take everything apart and I number all the pieces with these tiny little 1/16 number stamps. Everything is numbered so that it goes back into the exact same place and orientation on the locomotive every time. Once you've got everything fitting, you got to make sure that it stays in the right position. Then finally, I do some sanding on these parts because they are going to be visible, so I want them to look nice. I do some 320 grit paper to get rid of the tool marks. And then I also do a little bit of work with a red Scotch-Brite wheel on the rotary tool to give everything kind of a nice satin finish, not a mirror polish like you'd get with a buffing wheel. Locomotives work for a living, they ain't jewelry. With the diagnostic chooching out of the way, now we can do some recreational chooching. This is much more fun. Everything is moving very, very smoothly here. I'm going to need more track pretty soon. This little chunk of test track on my bench is not really enough to have the full chooching experience. There is a rolling road in my near future on this project. Well, there you go, the crosshead guide rails and a little window into the diagnostic process that goes into these complex mechanisms. Like I said, no matter how good a machinist you are, you start bolting all these pieces together, there's going to be some issues here and there. I'll use racing as a metaphor because, of course, racing is a metaphor for everything. The difference between a fast driver and a slow driver is 5 or 6 seconds on a lap, let's say, which is an eternity in racing. But that 5 or 6 seconds is a tenth of a second, milliseconds even, per corner. But over 10, 15, 20 corners on a lap, that adds up to 5 or 6 seconds. It's the same thing here when you're building a complex mechanism like this. If you're out by even a tenth on any dimension anywhere along the way, all of those errors can accumulate to where you've got a couple of components that are quite a bit of a ways out, and things start binding up. Now, of course, some of those errors are going to cancel out. In my case, they seem to inevitably conspire against me and all err in the same direction to cause massive issues, but your mileage may vary. Hopefully this was an educational exercise and we've got some pretty quality chooching starting to happen now. Thank you very much for watching. Thanks to my patrons for making all of this happen, and I'll see you next time.